Okay, I'm sorry. I have to give this to you. I looked at it. Basically okay, except I didn't understand it the first time. Okay, good morning. Happy spring. Happy April. We're running a little late. I'll try to finish Chapter 9 today and start on Chapter 10. Ashish may have Chapter 10 here later. If not, it'll be on the web. So we've been talking about convolutional codes, specifically rate 1 over n convolutional codes, 1 input, n outputs. As you may imagine, there are also rate k over n convolutional codes, generalization to k inputs, n outputs. These have not been so much used in practice because in general we're using these binary codes in the power limited regime and we want low rates. So 1 over n is a good rate. 1/2, 1/3, 1/4, or down to 1/6 are common kinds of rates. So I haven't bothered to develop the more elaborate theory for rate k over n codes. For rate 1 over n codes, just to review, the code is simply defined as the set of all possible output sequences of a convolutional encoder whose n impulse responses are written as an n-tuple g of d as the inputs range over all Laurent sequences, bi-infinite sequences. And what we showed last time is that without loss of generality or optimality, we could always take this g of d to be of a particular canonical form. Namely, the g of d could be taken to be a set of n polynomials, gj of d, that were relatively prime. And for any code, you can find such a canonical encoder. It's unique up to units and specifies the code clearly by this. So that's a nice canonical encoder to take. It furthermore has the property that there's an obvious realization of this encoder in the shift register form with new memory units, and therefore 2 to the new states. And we will prove in Chapter 10 that this is the minimal possible encoder for this code. In other words, there are lots of different encoders that generate this code, but you can't possibly encode it with fewer than a state space of dimension less than new. All right, that's the way it's going to sound in Chapter 10. So we haven't quite got there yet, but it's a minimal encoder, therefore, in that sense. All right, today we're going to go now and exploit the finite state structure of this code to get a very efficient maximum likelihood sequence decoding algorithm called the Viterbi algorithm, which I'm sure you've all heard of. It's become very famous not only for in this field, but really in any place where you're trying to observe a finite state machine in memoryless noise, a finite state hidden Markov model, if you like. And so now it's used, for instance, in detection of genomes where the exons end and the introns start and so forth, and the garbage is. And you know, people use it who have no idea that it was originally a digital communications algorithm. But it's a very obvious algorithm. It's come up in many different forms, and Viterbi, in a way, was just lucky to get his name put on it because it would come up very easily as soon as you pose the problem correctly. Let's start out with terminated convolutional codes, which I forget whether I started in this last time. I think I may have. But we'll start from scratch again. When I say terminated, I mean that we're going to take only a subset of the code words that start at a certain time, say time 0, continue for some finite time, and then end. And in this setup, with this canonical encoder, it's polynomial, the easy way to specify that is to let u of d be a finite sequence that starts at time 0. That's called a polynomial. And let's restrict its degree of degree u of d less than k. In other words, it looks like u0 plus u1d plus so forth up to uk minus 1d. Therefore, I've chosen k, so I really have k information bits, or input bits. All right. So I specify u0 through uk minus 1. I use that as the input in my encoder. What is then my code? My truncated code, let's call it CK. That's not a very good notation, but we'll use it just for now. Will be this set of all u of d, g of d, such that u of d is polynomial, and the degree of u of d is less than k. Okay, so we ask what that code is going to be. And let's take some simple examples. Turns out when we terminate codes, we always choose polynomial encoders, so that the code will naturally collapse back to the 0 state. How long? New time units after the input starts coming in, stops coming in. The outputs will be all 0 at that point and forevermore. The shift register will clear itself out new time units later, and then they'll be all zeros. So the code really starts at time 0 and ends at time k plus new. So we aren't going to worry in this case whether the code is non-catastrophic or not. Here, one of the principal properties that we had was that this property guaranteed non-catastrophic. And in fact is necessary for non-catastrophicity. So we spent a lot of time talking about why that would be a bad thing to be catastrophic. Okay, but let's take a catastrophic rate 1 over 1 encoder, in which simply we have g of d equals 1 plus d. You remember this encoder as new equals 1. The input looks like this, uk minus 1. And we simply add these and we yk. So we get y of d equals 1 plus d u of d. Okay, now if the input to this is a finite sequence, a polynomial, let's see what this code can possibly be. What the code's going to look like. The code's going to start in state 0 at time 0. So here's the time. At the first time, we can either get a 0 in or a 1 in, and accordingly it'll go to state 0 or 1. At the second time, we can go to state 0 with another 0, or to state 1 with a 1. If we get a 1 in, and we're in state 1, then the output is going to be 0 and we'll stay in state 1. If we get a 0 in, the output will be a 1 and we'll go back to state 0. So this is what a typical Trellis section looks like here. We have all possible transitions between the two states. And so now it goes on for a while like this, time invariantly, 0, 1, dot, dot, dot. And then finally, at some time, say this is time k, or maybe it's time k minus 1. Time index is always a little fuzzy here. We don't put any more ones in. We only put zeros on from that time forward, so we could have one more transition back to state 0, and then after that it just stays in state 0 forevermore. And this isn't very interesting. It was in time 0 all the time before here. It was in state 0 all the time before there and put out zeros. It was in state 0 all the time after here and put out zeros. And this is clearly not conveying any information, not an interesting part of the code. So we're going to consider the code just to be defined over these k plus 1 units of time. And so y of d we're going to consider to be a polynomial of degree k. In other words, we're going to assume that there are k bits in. Then we're going to wait one more time to let the shift register clear out, which is new. And at that time, we're going to take whatever y is, and then we're going to terminate it. So we really have, if we consider this now, we have a block code whose length is the number of non-zero coefficients of y of d. So we have n equals k plus 1. We have k by design information bits. And what's the minimum non-zero weight of this? It's linear. Well, what's its minimum non-zero weight or its minimum distance? 1. Show me a code word of weight 1. I claim the minimum non-zero weight is 2. My typical argument, I have the all-zero sequence. If I ever leave the all-zero sequence, I accumulate 1 unit of Hamming weight. And I need ultimately to come back to the all-zero sequence because I've made everything finite here. So in this case, I can make the argument that I always have to come back to the all-zero sequence. Whenever I merge back into the all-zero sequence, I'll accumulate another unit of weight. So this is a code with minimum distance 2, minimum non-zero weight 2. And in fact, it's just the single parity check code of length n equals k plus 1. Okay? And if you ask yourself, can you generate any, this is supposedly the even weight code. It contains all even weight k plus 1 tuples. And I think you can convince yourself that you can generate any of these k plus 1 even weight k tuples. In fact, the generator matrix for this code, look, here's a set of generators. 1, 1 is in the code. 0, 1, 1 is in the code. 0, 0, 1, 1 in the code. So here's a set of generators. 0, 1, 1. Generator matrix for the code looks like this. We just go like that, and with these k generators, you can generate any even weight code word. All right. So we get a kind of convolutional or form to the generator matrix, a sliding parity check form to the generator matrix. Okay, so I assert that this is the single parity check code. So here's a trellis representation for a block code. Yeah. Because I'm sure I've got the time indices screwed up, but I put in k bits. I wait one more unit of time, new equals 1, for this to clear out, so I get out k plus 1 bits. Think of it in terms of this here. I put in k. The last input you can think of as necessarily being 0, and I take the outputs here for k plus 1 times. Okay, so first of all, a couple of points here.
In general, the length will be k plus nu.
In general, the length will be k plus nu. So let's write that down. So in general, by terminating a rate 1 over n. Nu is called the constraint length. Constraint length nu, or 2 to the nu state code, convolutional code, after k inputs, we get a binary linear block code whose parameters are, we have k information bits, we have k plus nu non-trivial output times. At each output time I get n output bits, so it's n times k plus nu is the total effective length of the code. And the distance, we would have to say, is greater than or equal to the distance of the block code is greater than or equal to the distance of the convolutional code. Why? Because all of the words in this block code are actually sequences in the convolutional code. I'm assuming here that the code is not catastrophic, so that it's sufficient to look at all the finite sequences in the convolutional code. All right, and in general, the block code distance is almost always going to be equal to the convolutional code distance. And this is just for finite code words. So, as another example, suppose we take our standard rate 1/2, nu equals 2, distance equals 5, convolutional code. Our example 1 that we've been using all along. Suppose I terminate with k equals 4. Then I'm going to get what? I'm going to get a 2 times 6. I'm going to get a 12, 4, 5 binary linear block code. This is not so bad. Actually, there's a point that I'm not going to make very strongly here, but terminated convolutional codes can be good block codes. Linear block codes. And in fact, asymptotically, by choosing the parameters correctly, you can show that you can get a random ensemble of terminated convolutional codes that is as good as the best possible random ensemble of block codes. So terminated convolutional codes is one way of constructing optimal block codes in the asymptotic limit. These parameters aren't bad. Here's a rate 1/3 code with distance 5, not too long. You might compare it to what? The BCH code. There's a 1575 BCH code, which is clearly better because it's higher rate. But if you shorten this code, you have to shorten this by 3 to keep the distance. You would get this same code. So, it's not optimum, but it's not too bad. And furthermore, from this construction, you get a trellis representation, which in this case would look like this. It looks like the trellis that we started to draw last time. Sorry, it doesn't look like that. This guy goes down here. This guy comes here. This guy goes here. This continues for a while. And then finally, when we start to enforce all zeros, we only have one possible output from each of these. And we get a trellis that looks like that. All right, which is 1, 2, 3, 4. I did it correctly for this code, actually, because each of these is going to have a two-tuple output on it. All right, it's going to look like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Here, each of the information bits causes a two-way branch, no matter where you are in the trellis. So here's 1, here's 2, here's 3, here's 4. That's the end of them. We wait for new equal 2 to let the states converge back to 0. All right, so that's a trellis representation of this 1245 block code. Okay, I want to talk about terminated block codes, terminated trellis codes, convolutional codes as block codes for two reasons. One is to say we can get good block codes that way, but the other is to introduce the Viterbi algorithm for terminated convolutional codes. I think it's easier first to look at how the algorithm works when you have a finite trellis like this, and then we'll go on and say, well, how would this work if we let the trellis become very long, or in principle infinite? Would the Viterbi algorithm still work? And it becomes obvious that it does. So this is going to be a maximum likelihood sequence detection or decoding algorithm. We're going to assume that each time here we get to see two things, all right, corresponding to the 2 bits we transmit. So we transmit yk according to which trellis branch we're on, or y0 at this point, and we receive a two-tuple r0. If we were on a binary input additive white Gaussian channel, this would go into actually the 2PAM map, 2 plus or minus alphas, and be received as 2 real numbers. All right? And we do the same thing here. Y1, we receive R1 and so forth up to yk plus nu, or k plus nu minus 1, I think it is, or k plus nu minus 1. Okay, so we have a transmit two-tuple and a receive two-tuple every time, and we're going to assume that the channel is memoryless so that the probabilities of receiving the various possible received values, the likelihoods, are independent from time unit to time unit. That's the only way this works. Then if I want to get the total probability of R given Y, where now I'm talking about over the whole block, this factors into the probabilities of RK given YK, yes? That's what I'm going to depend on. This is what's called the memoryless condition, memoryless channel. The transition probabilities do not depend on what's been sent or received in previous blocks. Or it's more convenient to use the minus log likelihood equals now the sum of the minus log P of RK given YK. So maximum likelihood is equivalent to minimize the neg log likelihood. Okay, I receive only one thing in each time unit, and each trellis branch corresponds to transmitting a specific thing. So I can label each trellis branch with the appropriate minus log P of Rk given Yk. Do you see that? In other words, for this trellis branch down here, which is associated with y2 equals 0, 1, or S of y2 equals alpha minus alpha, suppose I receive R2 equals R1, R2, I would label this by, say, the Euclidean distance between what I transmitted for that branch and what I received. So for instance, on the additive white Gaussian channel, this would simply be Rk minus S of Yk, the Euclidean distance squared. Or, equivalently, minus the inner product, the correlation between Rk and S of Yk. We know these are equivalent metrics. Or on a binary symmetric channel, it might be the Hamming distance between what I received and what I transmitted, both of which would be binary two-tuples in this case. All right. It's just some measure of distance, log likelihood distance, Euclidean distance, Hamming distance, between the particular thing I would have transmitted if I'd been on this branch and the particular thing that I actually did receive. So having received a whole block of data, I can now put a cost on each of these branches. What's the minus log likelihood cost if I say that the code word goes through that branch? What does it cost me? All right. Now, what I'm basically depending on is, note there's a one-to-one map between code words Y in C and trellis paths. For this specific trellis up here, how many paths are there through the trellis? Do you see that however I go through the trellis, I'm going to meet 4 two-way branches? All right, according to how there are 4 yes-no questions. It's a binary tree, so there are 16 possible ways to get through this trellis from start to finish, if I view it as a maze problem. All right, and they correspond, I haven't labeled all the branches, but they do correspond to all 16 words in this block code. All right. So now what is maximum likelihood decoding? I want to find the one of those 16 words that has the greatest likelihood or the least negative log likelihood over all of these 12 received symbols, or 6 received times. So what will that be? Once I've labeled each of these branches with a log likelihood cost, I simply want to find the least cost path through this trellis, and that will correspond to the most likely code word. This is the essence of it. Do you all see that? The independent transmission allows me to break it up into a symbol by symbol or time by time expression. So I can simply accumulate over this sum right here. All right, and I'm just looking for the minimum sum over all the possible ways I could get through this trellis. All right. So now we translated this into a minimum cost, finding the minimum cost path through a graph with a very special structure, nice regular structure. Okay, once you've got that, then I think it's very obvious how to come up with a nice recursive algorithm for doing that. Here's my recursive algorithm by I'm going to start computing weights. I'm going to start here. I'm going to assign weight 0 here. Right here, I'm going to assign a weight which is equal to the cost of the best path to get to that node in the graph. In this case, it's just the cost of that branch. Similarly down here. Similarly, I proceed to these 4. There's only one way to get to each of these 4, and I simply add up what the total weight is. Now, here's the first point where it gets interesting, where I have 2 possible ways to get to this node. One way is via these 3 branches, and that has a certain cost. Another way is via these 3 branches, and that has a certain cost. Suppose the cost of this branch, of these 3 branches, is higher than the cost of these 3 branches, just pairwise. All right. Claim that I can pick the minimum cost path to this node, throw away the other possibility, and I can never have thrown away something which itself is part of the minimum cost path through the whole trellis. All right. Clearly, suppose the minimum cost, suppose this is the best path from here to here, this is worse, x. And now I find the minimum cost path through the whole trellis goes through this node. Say it's like that. Could it have started with this? No, because I can always replace this with a path that starts with that and get a better path. So at this point, I can make a decision between all the paths that get to that node and pick just one, the best one that gets to that node. And that's called the survivor. This is really the key concept that Viterbi introduced. All right? We only need to save one, the best up to that time. We need to do it for all the 2 to the new possibilities. So we have 2 to the new survivors at time k, or time I, whatever your time index is. I used k for something else. Okay, so I can throw away half the possibilities. Now, each survivor, I remember what its past history is, and I remember what its cost is to that point. Now, to proceed, the recursion is to proceed 1 time unit ahead, to add the incremental costs. Say, to make a decision here, I need to add the incremental costs to the 2 survivors that were here and here. So I add an incremental cost according to what these branches are labeled with, and now I find the best of these 2 possibilities to get to this node. So the recursion is called an ACS operation. For add, we add increments to each of these paths. We compare which is the best, and we select the best one. We keep that, we throw away the other. We now have a 1 unit longer best path to this node and its cost for all 2 to the new survivors at time I plus 1. Okay? And just proceeding in that way, we go through until we finally get to the terminating node. And at this point, when we've found the best path to this node, we found the best path through the whole trellis. Okay, so that's all it is. I believe it's just totally obvious once you reduce it to a minimum cost search for a minimum cost path through the trellis. Just a nice way of, it's very well suited to the application of convolutional codes because we really are thinking of sending these bits as a stream in time. And at the receiver, you can think of just proceeding forward 1 unit of time, do 2 to the new, add, compare, selects, and we've got a new set of survivors. There are nice implementations of this that involve, you can build a computer for every node or for every pair of nodes to do the ACS operation and make a very fast recursion through here. All right. So that's it. That's the Viterbi algorithm for terminated convolutional codes. Now let's ask about the Viterbi algorithm for unterminated convolutional codes. Suppose this trellis becomes very long. It's going across the whole page. What are these survivors going to look like? Suppose we start, from a definite node here, and we've got a 4-state convolutional code, and we iterate, and we iterate, and we iterate with the Viterbi algorithm. After a long time, somewhere out here, we're going to have 4 survivors, and their histories. And I've greatly simplified, but basically the histories are going to look schematically something, I don't know, could be anything. Look like this. The point I'm illustrating here is that the histories will be distinct right at this time. They have to be because they're going to 4 distinct stages. But as you go backwards in time, you will find that they merge. Any 2 histories will merge at a certain time back. And this is a probabilistic thing. It depends on what's happening on the channel and so forth. But with high probability, they will have merged not too far back in time. So even if we never get to a final node, even if we just let this process continue forever, at this point we can say we can make a definite decision at this time. Right? Because all survivors start with a common initial part up to here. All right, so one way to operate the Viterbi algorithm would be just to, at this point, say, okay, I'm going to put out everything before this time. That's what no matter how long I run the decoder, the first part of it is always going to be this part. So these are definitely decided up to this time. And then I still don't know about here. I'm going to have to go a little bit further. All right, you proceed further, and after a while you find more that's definitely done. In practice, that would lead to a sporadic output rate. That isn't really what you want. So in practice, what you do is you establish a decision delay delta. And what you put out is you hope that 99.999% of the time that if you look back delta on all the survivors, they will all be a common path, delta back here. It's with very high probability you will have converged. And so you simply at this time you put out what you decided on, delta time units earlier. Next time you put out the next one. Next time you put out the next one. So you get a nice regular synchronous stream of data coming out here. Every so often it may happen that you get out to here and you still haven't made a decision. All right, then you have to do something. And it really doesn't matter terribly much what you do. You might pick the guy who has the best metric at this time, or you simply might say, well, I'm always going to pick the one that goes to all zeros. That wouldn't be symmetric. Or you can make any decision you like. And you could be wrong. But you pick delta large enough so that the probability of this happening is very rare, and this just adds a little bit to your error probability, and as long as the probability of making error because of this kind of operation is much lower than your probability of making ordinary decoding error, then you're going to be okay. For convolutional codes, way back at the beginning of time, people decided that a decision delay of 5 times nu, 5 times the constraint length, was the right rule of thumb. And that's been the rule of thumb for rate 1 over n codes forever after. The point is delta should be a lot more than nu. After 1 constraint length, you certainly won't have converged. After 5 constraint lengths, you're highly likely to have converged. And theoretically, the probability of converging goes down exponentially, of not converging goes down exponentially with delta. So big enough is going to work. And a final point is that sometimes you really care that what you put out be a true code word. in that case, if you get to this situation, you have to make a choice. You make a choice here. Then you have to actually eliminate all the survivors that are not consistent with that choice. And you can do that simply by putting an infinite metric on this guy here. And then he'll get wiped out as soon as he's compared with anybody else. All right. And that will ensure that whatever you eventually put out, you keep the sequence being a legitimate code sequence. That's a very fine point. Okay, so there really isn't any serious problem with letting the Viterbi algorithm run indefinitely in time once you've got it started. How do you get it started? Suppose you came online and you simply had a stream of outputs transmitted from a convolutional code over a channel, and you didn't know what state to start in. How do you synchronize to a starting state? Well, this is not hard either. Basically, you start, you're in one of 4 states, or 2 to the new states. You don't know which one. Let's just give them all cost 0 and start decoding using the 4-state trellis. And this, we just start receiving 2 tuples from here on. We get rk plus 1, so forth. So how should we start? Well, we'll just start like that. And we get sort of the mirror image of this, that these, after a time, these will all converge to a single path. Or after a time, when we're way down here, this is what the situation will look like. These things will each have a different root over here, but they will have converged in here. There will be a long path over which they're all converged, and then towards the end, they'll be unrooted again. Okay, well, that's fine. What does that mean in practice? That means we make errors during the synchronization, but with we say we're synchronized when we get this case where all of the paths going to all of the current survivors have a common central stage. And how long does it take to synchronize? Again, by analysis, it's exactly this same delta again. The probability of not being synchronized after delta goes down exponentially with delta in exactly the same way. It's just a mirror image from one end to the other. So from a practical point of view, there's just no problem in just starting the Viterbi decoder up with arbitrary metrics here. And after 5 constraint lengths, if you like, it's highly likely to have gotten synchronized. So you make errors for 5 constraint lengths, and after that you'll be okay, as though you knew the starting state. All right? So the moral is no problem. You can just set up the Viterbi algorithm and let it run. You don't want the costs will all, of course, increase without bound, but as long as you can always renormalize them, subtract a common cost from all of them, that won't change anything. Keep them within running time. So we don't need to terminate convolutional codes in order to run the Viterbi algorithm. We just let it self-synchronize, and we make decisions with some decision delay. And the additional problems that we have are very, very small if we do this. There are no additional problems. Yeah?
Just choose the best path at the point of synchronization, like the best experience.
At this point? Well, notice that we don't know that we synchronize until we've continued further, and we've got, where we've really synchronized is when we see that every survivor path has a common root. All right. So at that point, there is really only one path here. And we can say that the synchronized part is definitely decoded. And we can't really say too much about this out here because this depends on what's happened out in the past. So we just say this is erasures, if you like. This stuff that we're pretty sure has a high probability of being wrong. There is only one error. There is only one decoded path for this during this interval.
But before that interval, there are branches and so on, right?
Well, here we don't know anything. Here we know the results of one computation. What are you suggesting? Just pick the best one at that point?
And finally, after you reach the synchronization.
And finally, I'm just not sure exactly what the logic is of your algorithm. It's clear from this it wouldn't make any difference if we just started off and arbitrarily said we're going to start in the zero state. And we only allow things that start in the zero state. Well, we'll eventually get to this path anyway. So really it doesn't matter how you start. You're going to have garbage for a while, and then you're going to be okay. There's no point in doing anything more sophisticated than that. I don't want to discuss what you're suggesting because I think there's a flaw in it. Try to figure out what time you're going to make this decision at. Okay, so do we all understand the Viterbi algorithm? Yes, good. We could easily program it up. There'll be an exercise on the homework, but now you could all do the Viterbi algorithm. All right, so, what's the complexity of the Viterbi algorithm? What is the complexity? We always want to be talking about performance versus complexity. So it's a recursive algorithm. We do exactly the same operations every unit of time. What do the operations consist of? They consist of add, compare, select. How many additions do we have to make? The additions are basically equal to the number of branches in each unit of time in the trellis, which is 2 to the new plus 1. Is that clear? We have 2 to the new states, 2 branches out of, 2 branches into each state, always for rate 1. So we have 2 to the new plus 1 additions. We get 2 to the new compares, 1 for each state, which is really, you can consider the select to be part of the compare. Overall, you can say the complexity is of the order of 2 to the new, or 2 to the new plus 1. This is the number of states, or the state complexity. This is the number of branches. I will argue a little bit later that the branch complexity is really more fundamental. You've got to do at least one thing for each branch. All right, so in different setup, the branch complexity, but these are practically the same thing, and so we say that the complexity of the Viterbi algorithm is basically like the number of states. If we have a 4-state encoder, the complexity is like 4. It goes up exponentially with a constraint length. This says this is going to be nice as long as we have short constraint lengths. For longer constraint lengths, constraint length 20 is going to be a pretty horrible algorithm. So we can only use the Viterbi algorithm for relatively short constraint length codes, just relatively small numbers of states. The biggest Viterbi algorithm that I'm aware of has ever been built is the 2 to the 14th state algorithm, the so-called big Viterbi decoder out at JPL that was used for the Galileo space missions. It's an Iraq that big. I'm sure nowadays you could practically get it on a chip, and you could maybe do 2 to the 20th states. But, so this exponential complexity in computer science terms, not really what we want. But when we're talking about moderate complexity decoders, these really have proved to be the most effective and become the standard moderate complexity decoder. The advantage is that we can do true maximum likelihood decoding on a sequence basis, using soft decisions, using whatever reliability information the channel has, as long as it's memoryless. So last topic is to talk about performance. how are we going to evaluate the performance of convolutional codes? You remember what we did on block codes? We basically looked at the pairwise error probability between block code words. We then did a union bound based on the pairwise error probabilities, and we observed that the union bound was typically dominated by the minimum distance error events, and so we got the union bound estimate, which was purely based on the minimum distance possible errors. And we can do exactly the same thing in the convolutional case. Convolutional case, again, is a linear code. That means it has the group property, has a symmetry such that the distances from every possible code sequence to all other code sequences are going to be the same. It's just we're talking on a long or possibly infinite sequence basis. And we need to be just a little bit more careful about what an error consists of. We need to talk about error events. And this is a simple concept. Let us again draw a path corresponding to the transmitted code word. Very long path, potentially infinite, but it is some definite sequence. And let's run it through a memoryless channel, use the Viterbi algorithm, and we're going to get some received code word, or decoded code word. This is one place where you might want to insist that the Viterbi algorithm actually put out a code word. What is that going to look like? Well, if you're running normally, the received code word is going to equal the transmitted code word most of the time, except it's going to make errors. And what will the errors look like? They'll look like a branch off through the trellis and then eventually a remerging into the same state. And similarly, you go on longer and you might have another error. And any place where there's a difference, should have done a different color here. Any place where there's difference, this is called an error event. So what I'm illustrating is a case when we had two disjoint error events. Is that concept clear? We're going to draw the trellis paths corresponding to the transmitted code word and the decoded code word. Wherever they diverge over a period of time, we're going to call that an error event. But eventually they will reemerge again. All right, so it could be short time, can't be any shorter than the constraint length plus 1. That would be the minimum length error event. Could be a longer time, unbounded actually. Okay, what is going to be the probability of an error event starting at some time? And when I say an error event starting at time k, let's suppose I've been going along the transmitted path and the decoder has still got that there. What is the probability? I'm asking, what is the probability that this code word is actually more likely on a maximum likely sequence detection basis than this one? Well, simply the probability that the received sequence is closer to this one than this one. All right, we know how to analyze that for finite differences. What is the difference here? The difference, call this y of d, and this y hat of d. What is y of d minus y hat of d? We'll call that e of d. This is a code word. This is a decoded code word. So the error event has to be a code word, right? The decoder made a mistake. The mistake has to be a code word. So we're asking, what is the probability that y of d sent, y hat of d decoded, where y hat of d equals y of d plus E of D. We'll just ask for that particular event. This is the probability that R of D closer to Y hat of D than Y of D. Now, making a big leap, this is equal to, we're just talking about two sequences in Euclidean space. All that matters is the Euclidean distance between them. What is the Euclidean distance between them? It's 4 alpha squared times the weight of this error event, the Hamming weight of this error event. All right? And so if you remember how to calculate pairwise error probabilities, this is just alpha squared d over sigma squared, where d is the distance of E of d. The weight, the Hamming weight of E of d over sigma squared. Do you remember something that looked like that? So once again, we go from the Hamming weight of a possible error event to a Euclidean weight, which is 4 alpha squared times the Hamming weight. We actually take the square root of that, and we only need to make an error, a noise of half of that length, so that's where the 4 disappears. And we just get q of d squared over sigma squared, where d is the distance to the decision boundary. All right. Compressing a lot of steps, but it's all something you felt you knew well a few chapters ago. So the union bound would simply be the sum over all error events in the code that such that start, so E of D is, you want them to start at time 0, say. Let's ask for the probability of an error event starting at time 0. So we want it to be polynomial, have no negative, non-zero negative coefficients, and have the coefficient at time 0 be 1, or not 0. I'm doing this very roughly, of q to the square root of alpha squared times the weight Hamming of E of D over sigma squared. Just as before. So to get the union bound, we sum up over the weights of all sequences that start at time 0. Let's do it for our favorite example. Suppose g of d is 1 plus d squared, 1 plus d squared. Then what are the possible E of d's that I'm talking about? I have this itself, 1 plus d squared, 1 plus d squared. This is weight equal to 5. What's my next possible error event? It would be 1 plus d times this. So this is going to be a table. We have g of d, 1 plus d times g of d, which is equal to 1 plus d squared plus d cubed, 1 plus d cubed. That has weight equals 6. What's my next longer one? 1 plus d squared times g of d equals 1 plus d fourth, 1 plus d third plus d fourth. That has weight 6. 1 plus d squared times g of d. Hey, what is this? 1 plus d, this is 1 plus d plus 1 plus d plus d third plus d fourth. I may be making a mistake here. 1 plus d squared plus d fourth. It's hard to do this by hand after a while. Okay. In other words, we just start tabulating all the error events, which I can do in order of their the degree of u of d, always keeping the non-zero, the time zero term equal to 1. So this is the only one of length 1. This is the of degree 0. This is the only one of degree 1. There are 2 of them of degree 2. There will be 4 of them of degree 3, and so forth. So I can lay out what all the error events could be, and I look at what their weights are. Here's my minimum weight error event, and then I have 2 of weight 6, and so forth. So the union bound, I'd be adding up this term. I'd get 1 term where the weight is 5, 2 where the weight is 6. I don't know how many where the weight is 7. I happen to know there are only 2 weight 6 error events. And you simply have to find out what the weight profile is and put it in the union bound. Or you can use the union bound estimate, which is simply, let's just take k, n d, the number of error events of minimum weight d, times q to the square root of alpha squared d, where d equals min weight, over sigma squared. Okay, in this case, nd equals 1, d equals 5. Let me take this one step further. nd times q to the square root of, what is sigma squared equals n naught over 2, and EB equals n times alpha squared. The energy per transmitted bit is alpha squared. We're going to transmit n bits for every information bit. So plugging those in, I get 2d over n times EB over n0, which is again of the form nd q to the square root of 2 times the coding gain of the code times EB over n0. Bottom line is I get precisely the same performance analysis where I get a nominal coding gain of, in general, it's kd over n. If it were rate k over n code, since we're only considering rate 1 over n codes, it's just d over n. And we get an error coefficient, which equals the number of weight d code words starting at time 0. Of course, an error event could start at any time. If there are NDs starting at time 0, how many start at time 1? It's time invariant code. All right, so it's going to be the same numbers could possibly start at time 1. So what I'm computing here is the probability of an error event starting at a particular time. For this particular code, I have, what do I have? I have one event of weight 5. So the nominal coding gain is 5 over n, which is 2, which is 5 is 7 dB, 2 is 3 dB. So this is 4 dB. That's pretty good. Nominal coding gain of 4 dB with only a 4-state code. Obviously a very simple decoder for this code. And what is KD equals 1? That implies, again, we have the same argument about whatever the error coefficient is. You could plot this curve. The larger the error coefficient is, the more the curve moves up and therefore over. You get an effective coding gain, which is less. But this means, since it's 1, you don't have to do that. The effective coding gain is the same as the nominal coding gain. It's still 4 dB. So it's a real 4 dB of coding gain for this simple little 2-state code. This code compares very directly with the 844 Reed-Muller code, block code. This code also has rate 1/2, it has the same rate. We'll see that it also has a 4-state trellis diagram. But it only has distance 4, which means its nominal coding gain is only 3 dB. And furthermore, it has 14 minimum weight words, which even dividing by 4 to get the number per bit is still a factor of 3. It's still going to cost us another couple of tenths of a dB. Its effective coding gain is only about 2.6 or 2.7 dB. All right, so this code has much better performance for about the same complexity as this code at the same rate. All right, and this tends to be typical. Convolutional codes just beat block codes when you compare them in this way. Notice that we're assuming maximum likelihood decoding. All right, we don't yet have a maximum likelihood decoding algorithm for this code. We'll find for this code we can also decode it using the Viterbi algorithm with a 4-state decoder comparable to this one. So we'll be able to say for maximum likelihood decoding we have about the same complexity, but we simply get much better performance with the convolutional. Yeah?
What happened to the K in the gamma C?
Say again?
What happened to the K?
Why is k equal to 1? Which k? Over here?
Yeah, K d by n implies d by n. How was that?
All right, we're only considering rate 1 over n codes. If it were a rate k over n code, we would get k over n because this would be n over k times alpha squared. Just the same as before. In fact, I just want to wave my hand and say everything goes through as before. As soon as you get the error event concept, you can reduce it to the calculation of pairwise error probabilities, and then the union-bound estimate is as before.
So why did you say that the error event cannot be nominal as a constraint?
Well, I have my little trellis here, and how long in real time does it take for 2 paths to merge? An error event has got to take at least nu plus 1 time units for 2 paths to diverge and then merge again in the trellis. Is that clear? Or put another way, the lowest degree of any possible error event is nu, which means it actually takes place over nu plus 1 time units. Okay, from this. Why is the lowest?
Degree of E of D.
I'm taking g of d to, the definition of nu is what? The maximum degree of g of d. Okay, so if that's so, then the shortest length error event is 1 times g of d, which takes nu plus 1 time units to run out. So error events have to be at least this long, and then they can be any integer length longer than that. Okay? You don't look totally happy. You understand?
I didn't
Okay.
see that diagram over there. From there, how do you see it? The same thing?
Excuse me?
How do you see that from that diagram which you drew?
How do I see it from this diagram? Where have I got a picture of a trellis? Here I've got a picture of a trellis. I've defined an error event by taking a transmitted code word. It's a code sequence. This is supposed to represent some path through the trellis. There's a 1-to-1 correspondence between code sequences and trellis paths. Then I find another code sequence, which is the one I actually decided on. I call that the decoded code sequence. And I say, what's the minimum length of time they could be diverged from one another? All right, let's take this particular trellis. What's the minimum length of time any 2 paths, say, here's the transmitted path. Suppose I try to find another path that diverges from it. Here's one, comes back to it. Here's one. Another one comes back to it. I say the minimum length of time it could take is nu plus 1. Why? Because the difference between these two paths is itself a code sequence, is therefore a non-zero polynomial multiple of g of d. Okay, same argument. Okay, so I guess I'm not going to get into chapter 10, so I'll discourse a little bit more about convolutional codes versus block codes. We have, how do you construct convolutional codes actually? You see that really what you want to do is to, first of all, maximize the minimum distance for a certain constraint length. Subject to that, you want to minimize the number of minimum distance words. It's the same as the, you want to, in fact, get the best distance profile. Is there any, block codes? We had nice algebraic ways of doing this, roots of polynomials, Reed-Solomon codes. We could develop an algebraic formula which told us what the minimum distance was. Do we have any nice algebraic constructions like that for convolutional codes? No. Basically, you just got to, you've got to search all the possible polynomials where the maximum degree is nu. Take pairs of polynomials. If you want to rate 1/2 code of degree nu, there's not that many things you have to search. All right, you just take all possible pairs of binary polynomials of degree nu or less, making sure that you don't take any two which have a common divisor, a non-trivial common divisor, so you can wipe those out. You want to make sure that the constant term is 1. There's no point in sliding one over, so it has a larger constant term than 1. But subject to those provisos, you simply try all pairs G1, G2, and you just do, as soon as you've assured yourself they're not catastrophic, they don't have a common divisor, then you can just list, the finite code words are going to be the ones that are generated by finite information sequences. So you can just list all the code words, as I've started to do up here. Or since the Trellis is in fact a way of listing all the code words, there's a one-to-one correspondence between code words and Trellis paths. You can just start searching through the Trellis, and you will quickly find all the minimum weight code words, and thereby establish the minimum distance, the weight profile as far out as you like, and you choose the best. You try all possibilities. So Joseph Odenwalder did this as soon as people recognized that short convolutional codes could be practical. And he published the tables back in his PhD thesis in '69, and so he got a PhD thesis out of this. It wasn't that hard. It's done for once and for all, and the results are in the notes, the tables. And you can see from the tables that in terms of performance versus moderate complexity, things go pretty well. Here's this 4-state code. It already gets you 4 dB of effective coding gain. To get to 6 dB of effective coding gain, you need to go up to about 64 states. First person to do this was Jerry Heller at Jet Propulsion Laboratory, again about 68, immediately after Viterbi proposed his algorithm in 67. Heller was the first to go out and say, well, let's see how these perform. So he found a good 64-state rate 1/2 code, and he did probability of error versus EB over N0, and he said, wow, I get a 6 dB coding gain. And Viterbi had no idea that his algorithm would actually be useful in practice. He was just using it to make a proof, and he didn't even know it was optimum. But he's always given the credit to Heller for realizing it could be practical. And so that 64-state rate 1/2 code with Viterbi algorithm decoding became very popular in the 70s. Heller and Viterbi and Jacobs went off to form a company called Linkabit. And for the technology of the time, that seemed to be a very appropriate solution. you'll see you get approximately the same thing as at rate 1/3, rate 1/4. If you go lower in rate, you can do marginally better. If you are after tenths of a dB, it's worthwhile. Later in the decade, is the best way to get more gain to go to more and more complicated convolutional codes? No. The best way is to use the concatenated idea. Once you use these maximum likelihood decoders, the Viterbi decoders, to get your error rate down to 10 to the minus 3 or something, 1 in 1,000, at that point you have very few errors, and you can apply then an outer code to clean up the error events that do occur. You see you're going to get bursts of errors in your decoded sequence. It's a very natural idea to have an outer code which is based on GF of 256, say, 8-bit bytes. And so a Reed-Solomon code comes along and cleans up the errors that do occur and drives the error probability down to 10 to the minus 12th, or whatever you like it, with very little redundancy, very little additional cost. So that became the standard approach for space communications in the 70s and indeed 80s. I've already mentioned that around 90 they went up to this 2 to the 14th state Viterbi decoder. They went to much more powerful outer codes, much cleverer, and they were able to get to within about 2 or 3 dB of the Shannon limit. And that was the state of the art on the eve of the discovery of turbo codes, which is where we're going in all of this. All right, so from a practical point of view, in the moderate complexity regime, simple convolutional codes with moderate complexity Viterbi decoding are the best still that anybody knows how to do. They have all these system advantages. They work with nice synchronous streams of traffic, which is what you want for data transmission. They use soft decisions. They use any kind of reliability information you have. They're not limited by hard decisions. They're not limited by bounded distance as the algebraic schemes are. So it just proved to be a better way to go on channels like the additive white Gaussian noise channel. Okay, so we didn't get into chapter 10. We'll start that next time.